Hey everybody, so today what we're going to do is we are going to learn how to take an equation that has multiple variables in it and solve for one of those variables. So let's first define it. An equation that has two or more variables is called a literal equation. And really all that means is that you've got some equation or formula that has multiple variables in it. And once again, what we're going to be doing today is finding out how to algebraically manipulate that equation so that you can solve or isolate one of the particular variables. So let's look at a little geometry problem here. It says, write a formula for the area of a parallelogram. Well, typically, when you think about the area of a parallelogram, you think base times height, right? And in this case, though, the area is 30 and the height is 5. We're going to call the base B here. So the general formula would be area equals base times height. Now we can substitute the values of the given variable. So the area is 30, so we're going to put 30 in for A. The B we don't know yet, and the height is given as 5 inches. A better way to write this would be 5B. So if we're going to solve this, it's pretty easy to solve for B here. You can clearly see that all we would really need to do here is divide both sides by 5, right? So if I start with 30 equals 5B, then divide both sides by 5, I get B equals 30 divided by 5 is 6. And so this is just a quick one-step problem, but what I want to show you is that we can actually solve for B from the very beginning. We don't need to plug in all the values up front. So let's start with A equals base times height. And if we're going to solve for B, really, when you're solving these literal equations for one of the variables, you're not going to do a whole lot different than you would just on a regular equation that we've solved before. In fact, we're going to do this exact same step. It's just we don't have a 5 here. We've got an H. So to solve for B here, we're going to divide both sides by H. H divided by H is going to be 1. So those will effectively cancel out. And so we'll be left with B equals the area divided by the height. So this is just an example of how we can take a formula or an equation that has multiple variables and solve for one of the variables. Oh, you can't see what I'm doing there. Sorry about that. So let's take a look at some other examples. Here we've got a bunch of equations with y and x, and for these we want to solve the literal equation for y. Now, if you've graphed linear functions before, you may recall that it's sort of useful to get them into a form that looks like y equals mx plus b. This is called slope-intercept form, and that's essentially what we're doing here. We're taking an equation that's not really in that form and trying to get it into that form. Now, we're not going to be graphing quite yet, but what we are going to do is practice our algebra to algebraically manipulate these equations and get them into that form. Solve for y, essentially. So with number 5, we got y minus 2x equals 15. So to solve for y, really we just need to move this term over to the other side. So we need to add 2x to both sides. And you can write this as y equals 15 plus 2x, that's fine. But I want you to try to get into the habit of putting it into that y equals mx plus b format. And what I mean by that is if you've got a term with x, let's put that one first. So 15 plus 2x can be written as 2x plus 15. And there we go. When it says solve for y, it just means try to isolate y, get y by itself. For number 6, we're going to do basically the same thing. Subtract 4x from either side. That leaves me with y equals not 4x, so we're subtracting 4x, so negative 4x plus 10. If you were to have written like y equals 10 minus 4x, that's not technically wrong. These are equivalent. Addition is commutative, so you can write the order of the terms in any way you want as long as they maintain their sign. However, just to kind of go back and talk about where we're going with this, we want to be able to get it into this slope-intercept form to make our graphing lives a little easier. So let's not write it like that. 7, it's kind of the same thing. The only real difference with number 7 is notice that we actually have a term with x on the right-hand side already. So, up here on 5 and 6, we didn't have one, so we just sort of wrote it explicitly, negative 4x plus 10. Here, we need to make sure to combine these correctly, right? So if I subtract 3x from both sides, that's going to leave me with 10x minus 3x is 7x minus 6. Now, if the variable you're trying to isolate has a coefficient in front of it, just like when we were solving regular equations, you just divide, right? The opposite of multiplication is division, so to undo this multiplication, we need to divide by 2. But when you do that, you have to make sure, and this is going to be one of those things that causes a lot of issues, is you have to make sure to divide everything by 2. Divide both of these terms. So just divide by 2 across the whole equation. So that would give me y equals 6 divided by 2 is 3, so 3x. 4 divided by 2 is 2, so you get 3x plus 2. So don't be tempted to just divide one of these by 2. You need to divide every single term. Now, we won't always be solving for y. Sometimes we'll be solving for x. So what you have to look out for is that there may be multiple terms that you have to combine. Or, like on the last one, we saw that on number 7, we had to combine them like this. But if they're already on the same side, then go ahead and just add them up, or subtract them in this case. So I'm going to start by combining my like terms just to simplify that right-hand side. You still want to look for opportunities to simplify before you really start solving. So y equals 5x minus 4x is just going to be 1x. So I'm just going to write x. And surprisingly, that's it, right? If there was some other coefficient here, we'd have to divide, but in this case, we do not. On number 10, we're solving for x. So solve the literal equation for x. So we need to start by adding y to both sides. That will eliminate it from the left-hand side. Negative y plus y is just 0. So we've got 3x equals, see, y minus 4. And then divide everything by 3. Now, if your terms are not actually divisible by whatever you're dividing by, there's 2 ways to write it, and I'm comfortable with y'all just leaving it like this. But if you were to try to divide it, 1 divided by 3 and 4 divided by 3 are just going to remain fractions. So an alternative way of writing this, so like another correct answer, and I don't really care which way you do it, would be to write, let's see, 1 divided by 3 would just be 1/3 y minus 4/3. So these look pretty different, but these are actually equivalent. So you can write it either way. This way is probably easier because you don't have to actually do any division or think about the fractions. But this looks a little nicer, yeah? Or at least I think so. That's kind of an opinion, and that's why I don't really care which way you do it. Let's look at number 11. This is where it starts getting kind of weird because it appears like we need to combine these like terms, right? They both have x. Like in the previous one, on number 9, we said 5x minus 4x is 1x. So I want to clarify how you combine these like terms when the coefficients are variables themselves. Well, just to work something similar out to the side, if I have something like 2x plus 7x equals r, right? So if I just had numbers here, this would be 2x plus 7x would be 9x, right? And a step that we don't typically write, and I'm going to write it this time, is to actually combine it like this. So 2 plus 7x equals r, right? This is going to end up being 9, which is what you would expect, right? 2x plus 7x is 9x. We don't really usually write this because when those coefficients are numbers, we can just sort of add them in our head most of the time or use a calculator to do it. But when they're variables, We can't really add them together. So this is a case where we really do have to show this step. And you don't have to do this when you're just solving a regular equation, but for literal equations, if you're trying to combine like terms and the coefficients are variables themselves, then you need to write it like this. So if I'm going to add tx plus mx, that's just going to be t plus m. Let's write that t so it doesn't look like a plus sign. So t plus m would be the new coefficient, right? I can't simplify it, but that's whatever that it adds up to be is going to be my new coefficient x. Now, once I get this down to 9x equals r, the way you would typically solve that is to divide both sides by 9 and you'd be done, right? You would have solved for x. And that's exactly what you want to do here. It's just that this can't be simplified, so you're not going to divide by a single number, you're going to divide by this whole expression. This is the coefficient to x. So we need to divide both sides by t plus m. Most of the time you're going to be pretty much done here because these will reduce to 1 and this can't be reduced or simplified, so your answer is just going to be r divided by t plus m. If you want to leave the parentheses you can, but whenever you have a fraction bar there are implied parentheses anyway, so you don't really need to write them. Let's do the same thing for 12. Right? We want to try to combine these like terms, but one of the coefficients is a variable. So, if this was like 2x plus 3x, we would write 5x. But we can't really add 2 plus k, can we? So we're just going to leave it as 2 plus k. Then divide. And that leaves me with x equals p over 2 plus k. That's your answer. Sometimes I feel like with these little equations that the solution's not very satisfying because it's kind of nice to get an answer here, like an actual number, but this is just going to be some expression. It's also kind of tricky to check these solutions too. When you solve a regular equation and you get something like x equals 5, you can always just go plug it in, plug it back into the original equation and make sure that it's true. And technically you can do that with this too, but it's definitely not as easy. It's not like you can plug this in the calculator. You really have to be able to simplify the expression to verify that both sides are the same. So that's gonna be a little hard. So whenever you're trying to show how one variable is related to another variable, we call that a formula. And this definition we use pretty loosely. We use the word formula when we don't necessarily mean a formula, but that's not that important. But really what we're going to do is look at these formulas that show us the relationship between like specific things and try to isolate one of the variables. So for instance, we have this formula. Distance is rate times time. Okay, this is something we might use later in the year. When you take physics, you'll use this a lot too. So if we want to find a formula for the r, or solve for r, or isolate r, all we need to do here is just divide both sides by t, which gives us r, these will reduce to 1, so r equals d over t. Here's a formula for interest. Interest equals principal times the rate times the time. You don't really need to know too much about this yet. We'll talk about this later in the year, but we're using it as an example to solve for one of the variables, in this case p. So we've got p times r times t. So if we want to get rid of this r and t and isolate p, we need to divide both sides by rt. You can do these at the same step. If you do it one at a time, that's fine, but you're probably better off just doing it all at once. So p, since all this reduces to 1, equals I over RT. The circumference of a circle is given as 2 times pi times the radius. And so if we want to solve this for the radius, we need to divide both sides by 2 pi. So this will all reduce to 1. We get r equals c over 2 pi. And finally, the area of a triangle. You're probably familiar with this equation. Area equals 1/2 times base times the height. We want to solve for b. So here, let's take care of this 1/2 first. We can solve it just like we did 14 and 15, where we divide by both 1/2 and h. But dividing by 1/2 is really just a more complicated version of multiplying by 2. So let's start by multiplying by 2. Again, you don't have to do these two steps separately, but when we're dealing with fractions, sometimes it's easier to just sort of isolate that particular step. So when I multiply both sides by 2, I get 2a equals base times height. And then if I divide by h, so that I can isolate b, I get the base equals 2 times the area divided by the height. And that's all for today.